So, one of your classmates, Sriram, he sent me an email yesterday pointing out something very important, that I use the concept of a sequence in the proof of the CSB theorem. Correct? A stopper sequences, doubly infinite sequences, and B stopper sequences. But we haven't really defined the concept, and this course is all about asking questions. So he asked the right question, that we haven't defined integers yet. So how can we use the concept of a doubly infinite sequence? So therefore here is a resolution. We can define the equivalence relation that we needed using this method. It's written on the board. This is an equivalence relation. You can verify that. So two elements are related if there exists a finite chain of f's and g's between them in some direction. Yeah, this is not really hard to write down. Yeah, it looks complicated on the screen, but it's not complicated at all. And then A stopper sequence is one which contains an element which doesn't lie in the image of G. B stopper sequence is one equivalence class which doesn't lie in the image of F, and an element in that equivalence class which doesn't lie in something particular. So that's how this proof can proceed. And I also forgot to mention that the proof that we covered in the class is due to Julius Koenig. Yeah. So somebody from your class also asked me if this proof ever uses the axiom of choice, yeah, which is a very controversial as well as the most interesting topic of the set theory part. Yeah, ZFC, as you might know, Zermelo-Frankel choice set theory. So this choice is an important topic which we'll cover later in the course, but this proof does not use any axiom of choice, any form of axiom of choice. Okay. Any questions about this? Okay, let's proceed then. So, all of you remember that we started with some of the axioms, and then I mentioned that there was an axiom of foundation. I am just going to talk about a bit of philosophy before we do something proper. So axiom of foundation, I am not going to write down the axiom, it's not really intuitive in the form it's presented, but it implies something important. Yeah, it implies that there is no, I mean, instead of there is no, we can perhaps say that each sequence of this relation is downwards finite. Okay, what do I mean by that? So I start with a set A0, then A0 contains A1, A1 contains A2, and dot dot dot. This dot 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 cannot happen, right? This so on process cannot happen. It has to end at some an, and that's a full stop. An itself cannot contain another element. For some an cannot contain an element, which means an has to be the empty set, right? So this actually gets rid of this normality. Yeah, in particular, A0 doesn't belong to A0, because if it did, then A0 belongs to A0 belongs to A0 belongs to A0, and then you can pull it down. It's infinite regression kind of situation. Yeah, you remember Munchausen's trilemma? Yeah, this is infinite regression, so we don't want that to happen. And also, yeah, we don't have any set sequences. Yeah, so suppose I am writing some element. So this element contains something else, and then this dot dot dot, and you continue. Yeah, you never actually specify the element which is there. Yeah, this contains this contains this contains this, and we are just going down. Well, this is also useless. So in our set theory, we assume that we don't have any such situation, and this is axiom of foundation. It says that set theory is well founded. Yeah, it's founded on a base of the empty set, which can be questioned, of course, that empty set is nothing, so everything is founded on nothing. But at least formally speaking, this is what we need. And I'm talking about this because today we want to discuss construction of some number systems. The first number system that comes to our mind is natural numbers. Yeah, natural numbers, then we have to define addition of natural numbers. Well, you might say we are being childish. Yeah, you already learnt addition in the primary school, but we have to redo it in a formal way. Addition, multiplication, exponentiation of natural numbers, yeah, all these things are important, and we are going to define them properly, right? So before we do that, we should first ask the question, what is addition? You take two elements from omega and you give one new element of omega. So basically we need a function which has two arguments which are natural numbers. So first of all, what is omega? And how can we define a function whose domain is omega or something infinite? So these are the two questions. So what is omega? Yes?
What is it actually a sequence of?
Is sequence of belonging relations. Belonging relation, yeah, decreasing sequence. Any decreasing sequence of belonging relation. So what is omega? We already said that omega is n, such that n is natural number. But we did not really define it properly, what is a natural number and whether we can do this. So there is some axiom which is called the axiom of infinity. So axiom of infinity, it guarantees existence of an infinite set. Without this, we cannot really define omega as a set. Guarantees the existence of an infinite set. See, so far what we have seen philosophically, that because of Russell's paradox, the collection of all sets is not a set. You remember that? Yes, so that is not a set. So similarly, if we don't assume axiom of infinity, then the collection of all natural numbers or collection of all finite sets itself will become a proper class. Yeah, take a moment to understand that. If we do not guarantee the existence of an infinite set, then the collection of all finite sets itself, yeah, you cannot really control it. Yeah, it's beyond control, so it is a proper class itself. So therefore, we need axiom of infinity which guarantees the existence of an infinite set so that we can deal with infinity, and we have pushed the problem further away from us. Yeah, the problem doesn't vanish, that the certain collection is not a set, that problem doesn't vanish, but we have just pushed the problem away from us. Understood the idea? Yeah, that after all levels of infinity, which we will define in the course later, after that there is something which is blocking our path, the collection of all sets, which is not a set. But if we just know the remaining axioms of Zermelo-Fraenkel set theory, without the axiom of infinity, then the natural numbers, this omega itself will become a proper class. So let us write down what is this axiom of infinity. Yeah, this itself is an interesting thing. So again, this is an existential axiom. It starts with there exists a z. This z is supposed to represent an infinite set such that empty set is in Z. Yeah, empty set is guaranteed by the axiom of empty set. Empty set is in Z, and for all x in Z, x plus is also in Z. Okay, what is x plus? I should simply write it down. You all know this. X plus is x union singleton x. We use it to define natural numbers, if you remember. Yeah, 1 was 0 plus, 2 was 1 plus, so n plus 1 is n plus. Yeah, it's the shift operator on natural numbers. So let us see what this statement means. So there exists a set which contains empty set, and whenever something is an element, then its plus is also an element. So empty plus is an element, then empty plus plus is an element, and so on and so forth. Right? It's guaranteeing something will continue. Are you understanding this? However, this is not just, this just guarantees the existence of some such Z. Yeah, this is not yet necessarily the collection of natural numbers. Can you see that? Maybe not yet, but when we'll do ordinals, you will be able to see that. Yeah, I mean, for example, 0, 1, 2, dot, dot, dot. Yeah, this is definitely collection of natural numbers, then omega plus 1, then omega plus 2, and dot, dot, dot. This is an infinite set. You understand omega plus 1? Yeah, omega plus 1 is omega plus. Then omega plus 2 is omega plus plus, and so on. So this is an infinite set. So this doesn't guarantee that omega exists. It just guarantees that some infinite set exists. Then there is another axiom which we use to cut it down to precisely the successors. I mean, this plus means successor. The successors of empty set. Yeah, successor of empty set is 1, 2, 3, like iterated successors. So actually, now I am going to write down the description of natural numbers. Let's do that. So y, I mean y is a natural number if, I mean, I am going to write down a big sentence. If y is equal to empty set, or there exists an x such that y is equal to x plus. Yes, this is true, this first part is true. Either a natural number is 0 or it is successor of something else, and moreover, right, so this is the first part, and for all x in y, either x is equal to empty set or there exists a z such that x is equal to z plus. So every element of the natural number is itself either 0 or it is a successor of something. So this particular formula, yeah, this is a logical formula. So this particular formula describes what is a natural number. All of you agree with this? I mean, at least can you understand that this defines a natural number?
Second part of
Right. So let us say we are working with 2. What are the elements of 2? 0 and 1. So 0 and 1 are themselves natural numbers. So the second part says precisely that. We are saying this is a natural number, it is either 0 or successor of something, and every element is also either 0 or successor of something. Means it is also a natural number. And this process is continued. Yeah, you keep checking this for the elements of elements of elements, which process, by the way, has to stop because of this, because of axiom of foundation. Now notice something, notice this particular element, yeah, this omega in our आज नहीं चाहिए, सिर्फ फ्राइडे को चाहिए, फ्राइडे 12 बजे. Yeah, this has become our running joke, right? When they are supposed to come, they don't come, and when they are not supposed to be here, they will be here. Okay, so look at this particular element omega. Is omega empty? No. Omega is not empty, and is omega a successor of something? Yes. No. Omega is not itself a successor of anything. Omega is the collection of all natural numbers. Omega plus 1 is the successor of omega. Correct? But omega itself is not a successor of anything. I mean, omega is like 0, 1, 2, 3, dot, 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 and after that dot, 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 there is omega. So, is there any immediate predecessor of omega? Right? It's a jump, a leap of faith, you may call it. Yeah, it's a jump from all natural numbers to the collection of natural numbers. So therefore, omega, if it is an element, then it is not an, omega as a set is not a natural number. So this narrows down our collection, like this formula indeed defines natural numbers. Yes?
So why is omega in the infinite set if omega is not a successor of something?
Because the concept of like this axiom of infinity doesn't really talk about the second part. Observe that. It just says that whenever there is an element, then its successor is also there. It doesn't put any condition on which element should be there. Are you getting the difference between these two statements? The first statement just says that either, so empty set is always there. So therefore, and whenever there is an element, then its successor is also there. So therefore, 1 will be there, 2 will be there, dot, dot, dots. All the natural numbers will be there for sure. Moreover, if there is some other element, then its plus will also be there, its plus will also be there. You just close it under successors. But you don't know about its history. Whereas being a natural number means that we are well founded at the empty set. We also know how to trace its history back to the empty set. Any other questions? Yeah, this is quite philosophical.
So we have not defined the set of all y.
No, this is omega. Omega is the collection of all such y's such that y is a natural number. And its existence as a set is guaranteed by the axiom of infinity and axiom of specification, which I don't want to talk about. Yes?
Why omega is not a natural number?
Because does it satisfy this first square bracket? Is omega empty? Is omega a successor of something?
Yes, sir, like if omega is up to 0, 1, 2 up to n. So we can
No, omega is not 0, 1, 2 up to n. Omega is 0, 1, 2 up to n and n plus 1 and dot, dot, dot. So it's dot, 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 that is the problematic thing. It's not really, it doesn't have a history. It doesn't have a predecessor, an immediate predecessor.
Basically, omega is
Omega is?
tending to infinity.
Oh, that kind of statement doesn't make sense in this class. What is the meaning of omega tending to infinity?
It has infinite elements.
Omega has infinite elements, yes.
So that's why it doesn't have.
But omega tending to infinity is not really a proper statement. Omega is a fixed set in Zermelo-Fraenkel set theory whose existence is guaranteed by the axiom of infinity and some other axioms. But do you understand that omega doesn't have a predecessor? It's not plus of anything. Okay, so now we have established what is the collection of natural numbers for the first time. Yes?
Sir, but omega is a successor.
Omega is a successor of what? Please tell me.
Omega has a successor.
Omega has a successor, yes. Yes, every set has a successor. Yes, because successor is simply defined to be you take x and then you take its union with singleton x. Now, this is certainly going to be larger than x. Yeah, with this definition, so x is, so clearly for any x, x is a proper subset of x plus. Can you see this? Why?
Because of the axiom of foundation.
Yes. By using the axiom of foundation. Because x itself is not an element of x, but it is an element of x plus. So therefore, we have a proper inclusion.
Sir, basically, do you want to say like omega is not a natural number, so omega plus 1 won't be a natural number, so it is not a set of all natural numbers. Do you want to say that?
Omega is defined to be the collection to the set of all natural numbers. Yeah.
So,
Omega plus 1 is also not the collection of natural numbers.
because omega is not a natural number.
I don't know how those two statements are related. See, omega is the collection of natural numbers. So there can only be one set which is the collection of natural numbers. So we have defined that. So obviously it cannot be omega plus. It cannot be omega plus plus. Yes, any question? You probably don't know how to phrase a question right now.
Sir, so this set 0, 1, 2, omega, omega plus 1, this is not a set of natural numbers.
No, that is not a set of natural numbers, but the set of natural numbers is a subset of this as well as element of this. Understood? This first part says that it is a subset, and this particular thing says that it's also an element. Yes?
Sir, I didn't understand how is it an element of this?
Because omega is the set of natural numbers, and omega is written in this list form. So therefore it is also an element.
So then what is omega plus 1?
What is omega?
Plus 1.
Omega plus 1 is omega plus.
So,
It is the successor of omega. So it contains 0, 1, 2, dot, 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 and then comma omega.
so then how do you define omega plus? Like,
Omega plus, see this definition is defined, this particular plus construction is defined for any set. X plus is defined for any set, no matter whether you are starting with a natural number or not. Because of axiom of foundation, x is not an element of x, and therefore we can construct x plus. We are allowed to do unions. Axiom of pairing guarantees that singleton x is a set. X is a set is given, singleton x is a set by axiom of pairing, and therefore x union singleton x is a set, and it is a proper superset of x. So it's a new set. Understood this part again? Any other questions?
so how do we show the uniqueness of omega?
Uniqueness of omega.
You are saying that there is only one omega, like.
There is only one omega. Okay, so that's called axiom of specification or replacement. So you actually cut down. So you start with any infinite set which is guaranteed by this axiom of infinity, and then you intersect it with the collection that we have here. You add this property in its definition, then you will always get just the omega. Yeah, so that's axiom of specification. It allows you to chop down some part of a set. But yeah, we don't want to discuss like very formal axiomatic set theory. This is semi-axiomatic set theory that we are doing. We are writing down some axioms, we are not writing down others.
So, but the axiom in infinity should be like it is 0, 1, 2 up to so on.
Axiom of infinity doesn't give this particular expression. I'm just saying there exists a set which has this property.
But 0 exists and 0 and then 0 plus exists, that is 1 exists.
0 plus, yes, x plus exists for every x.
So if 0 exists, 0 plus exists, then 1 plus exists and so on.
Yes.
It's just like, we have already defined natural numbers. So just like.
No. See, again, please look at this part. We are not only defining natural numbers, but this red underline just says that whenever you have an element, then its plus is also there. Okay, any other questions? We are spending half an hour just on this today. And I don't mind that because you have to understand these things.
So finally omega plus 1 is omega union singleton omega.
Omega union singleton omega. Yes, that's all. Right. Okay, let's proceed now. Now the second part is we now know what to do with the set of natural numbers. It exists, omega exists. Now we want to define a function on omega. Function on omega, yeah, with domain omega. So for example, I mean, of course we can say because it's a set, we know the collection of all functions from omega to any other set, right? So given a set X, we would like to define a function f from omega to x that can be described by a rule. Yeah, this I am going to leave undefined. That can be described by a rule. Can you guess what I am referring to?
The definition of function.
The definition of function by. So I start somewhere, yeah, for defining a map from omega to x, I start somewhere and then I always describe the next value in terms of the previous values. What is it called? Recursion. Are there any people who want to say induction? Is this called function definition by recursion or induction? Recursion. So yes, so by a rule is it stands for recursion. Now first of all you should understand the difference between recursion and induction. So recursion is used to define something for each natural number. Definition for each natural number. We are not trying to prove anything. Whereas induction is a proof for each natural number. So these two terms are different. Both of them have common features, that there will be a base case So, in induction we have to prove the statement, a certain property for the base case. In definition, in recursion we have to define it to be something specific for the base case, and then you have an inductive case or recursive case. Yeah, so the successor case. On both sides we have successor cases. So induction is a method of proof, recursion is a way to define certain things. So by a rule means by recursion. Okay. So any questions about this, recursion versus induction? These are just two different names, but many times, I mean, this is the first class I have seen where everybody agreed to recursion and not induction. Maybe some people did not know what to say. Okay, so now I am going to specify this particular, I will use a new page for this. So suppose X is a non-empty set. X0 is an element of X, and F, capital F from X to X is a function. Okay, so there is some endo function. Endo function means whose domain and codomain is the same. There is an endo function F on X. So the principle of mathematical recursion I am not going to prove this, but this is a theorem which we can prove. I am not going to prove it right now, and we will see in the future if it is necessary. So, given the above data, there exists a unique function small f from omega to x such that f of 0 is equal to x0 and f of n plus is equal to, not by definition, I will remove that, is equal to capital F of n.
There can be more than one base case.
There can be more than one base cases, yes. Of course, I am writing it in the simplest possible form right now. Yeah. There is also a general version which doesn't even use the base case, and yeah, we will perhaps do it when we study ordinals, because for ordinals we will need transfinite recursion and transfinite induction. So trans means beyond. So beyond finite we will define something over all ordinals and prove things for all ordinals. Okay. So this is the simplest possible case. Yeah, we are doing only one base case and then we are proceeding. So this actually defines a sequence. It's a recursive definition of a sequence, which is where our discussion started today. So f of 0 is x0. Then once you have x0, then the next sequence is, yeah, so this defines a sequence. So what is the sequence? X0, then f of x0, yes, then f square of x0 and dot dot dot. Now this particular theorem, the principle of mathematical recursion, gives meaning to this dot dot dot. Yes. So, do you understand that x0 is the value of little f of 0? That's there. Then capital F of x0 is the value of small f of 1. Then small f of 2 is equal to f square of x0 and so on. But this so on or dot 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 has to be mathematically specified. And this theorem, which is known as the principle of mathematical recursion, it actually gives meaning to this so on. Yeah, we can continue like this so that we obtain a function which is defined on entire of omega. It is defined for each natural number. If you want to do it on the domain which is finite, let's say 0, 1, 2 up to 100, then you don't need principle of recursion. You just do it one by one. However, if you want to do it for all natural numbers at the same time, then you need to resort to this statement. You understand this? Yeah, many times even if I write down its proof, the proof is not hard. But even if I write down the proof, then what really is the point is the main question. In mathematics, we can never leave anything undefined. We have to be very precise all the time. So that precision has to be also to be about this dot 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 that's so on. Yeah, we have to formalize this process that once you have defined a rule to obtain the next thing from the base case, then this actually defines a function on the entire omega. Okay, so it's not the principle itself is not hard, the statement is not hard, the proof is not hard, but the philosophical question is hard. Yes.
Sir, is it necessary to be only a single base case?
No, I already said that I am doing it for the simplest possible version. Yeah, there can be multiple base cases and there is a more formal version of this. I don't want to do it. Fibonacci, yes, Fibonacci sequence works with 2 base cases and we can generalize this, but this is the simplest version of principle of recursion. Right now just try to focus on what it wants to say, yeah, rather than the most general case. Yes?
So then we can redefine the definition of small f, like fn is equal to capital F n x naught, so that this dot 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 will be defined then.
Even if you define f of n plus is equal to capital F to the power n, n plus 1 perhaps, n f to the power n plus of x naught, once again, how do you make sure that all the powers, you can do it until a certain number. For any fixed number you can define that much power. Yeah, a capital F to the power 100, capital F to the power 1 million, you can do that. But the question is, does this rule allow you to define it for every natural number?
Like if we define for k equal to for k and then k plus 1, then it's true.
Yes, so that's my point, that it feels that we are not really proving anything, but just like we had to guarantee the existence of an infinite set, we have to guarantee the existence of a function which is defined on omega, an infinite set. You can do it for any natural number, but can you do it for all natural numbers at the same time? That's the real question. You understand the difference between any and all?
By induction, we can do it for all.
Again, yeah, you are using the word induction. Induction is used for proofs. We are not proving anything here. We are proving the existence of a function which is recursively defined, not inductively defined. Yes, so we have to be careful about language. We are defining a function, so it has to be recursion and not induction. Okay, enough of philosophy, let's do some example. Yeah, so choose x equal to omega, then x naught equal to a, yeah, a in omega, some particular a, it's our choice, and capital F from omega to omega is simply n mapping to n plus. Okay, what function little f is it trying to define? Okay, let me write it down. What is f of 0? A. And what is f of n plus? What is f of n plus? Use this definition. F of n plus is capital F of n.
F of n plus.
So this is f of n plus. So we are starting with a and every time we are adding 1. So what exactly are we defining? Therefore f of n is equal to a plus n, exactly. So that's how we define addition. Yeah, to do something so simple, we had a very long way. We are not defining addition as a binary function. Yeah, we are not taking two different values as input and spitting out the output. We are defining it as a sequence of functions which have only one variable. A is fixed here. For each a, we define it like this. Then again we can use principle of mathematical recursion to define it as a function of functions, yeah, where a is the parameter, and then that will become a two variable function. Too much? I will repeat. Yeah. So we can again use this a as our starting as our parameter of the function and choose a different x. X is the set of functions from omega to omega and a is the parameter, and then we will define it as a two variable function. Plus, yeah, I mean, see, ultimately plus is a function from omega cross omega to omega. Right now we are fixing this particular value and then defining a function. Then later on, once we have enough functions for each a in omega, then we can take the collection of all functions and define a sequence of functions to define this two variable plus. Right now we are just doing it for one. Okay.
So how do you know that capital F exists?
Capital F exists, I mean, this is a well-defined function. By axiom of infinity, this capital F from omega to omega is well defined.
So do we have to use the principle of
Okay, I understand your question. Principle of recursion, yes. Yes, by axiom of infinity, we can guarantee something like that. Yes. Yes, okay. I am going to write down one more thing. Yeah, so this is our first one. So we are going to choose x equal to omega. Okay, so this is first one. So choose x equal to omega, then x naught equal to 0, and also choose a in omega. Right, we are going to use that in the definition. And f from omega to omega now is defined to be n mapping to what? N plus a. Right? Then what will be f of n in this case?
A plus F of n.
Yes, so that will be you can verify this that it is actually the multiplication function a dot n. Yeah, because we are starting with 0. So f of 0 is 0, and then f of 1 is 0 plus a, f of 2 is 0 plus a, which is 2a, and so on. This is how you teach addition and multiplication to a computer. Okay? All those functions are already inbuilt. You think that they are inbuilt, but somebody has programmed these recursive definitions inside. Okay, one last thing. Third one, well, I want to define exponentiation. Tell me how to start. X equal to omega, x naught equal to 1. Very good. And f from omega to omega, it is defined to be n maps to n dot a, which we just defined. Yeah, so use that. Use addition to define multiplication. Use successor to define addition. Use multiplication to define exponentiation. Okay, then f of n will turn out to be a to the power n. Yeah, because a to the power 0 is indeed 1, and a to the power 1 is 1 dot a to the power 2 is a dot a, and so on. Okay, so we have defined 3 basic operations on natural numbers. We cannot define subtraction, correct? 2 minus 3 is not defined.
So actually we defined a dot n, not n dot a.
A dot n, no, yes, but that won't matter.
Like, yeah, we haven't shown they're equal.
Yes, so by induction we can show that addition is commutative, addition is associative, then multiplication is commutative, multiplication is associative, everything can be done. Okay, those are proofs by induction. If you want, we can do some of them in the future. Yeah, but I want to do the more general version. These versions you already know. We should do it for ordinals and not just for finite ordinals, which are natural numbers. Okay, so I had given you some homework. What is an equivalence relation? Can you just tell me? What's an equivalence relation? On a set, it is a binary relation. It is a subset of A cross A, which is reflexive, symmetric, and transitive. Okay, so these 3 properties are satisfied. And given any partition of a set, what is the partition? It is a collection of non-empty subsets such that every element of the set belongs to exactly one subset of that collection. Okay, so that's a partition. So partitions and equivalence relations are the same. Yeah, that's also one of the exercises on the tutorial sheet. There is one more part of this. And using equivalence relations on pairs of natural numbers, tomorrow we'll begin by defining the set of integers. Now we have at our hand addition, multiplication, and this. Oh, let me finish by just saying one line. Yeah, so the notation n refers to either omega with blank plus as the operation. This is an algebraic operation. So blank plus is a function from omega to omega, or omega then plus from omega cross omega to omega, then dot from omega to omega cross omega to omega, and yeah, I mean usually just these, and maybe sometimes exponentiation. So some algebraic operations defined on the set of natural numbers, then we refer to it as n. Whereas omega stands for the set of natural numbers with less than relation, or the relation less than relation is also same as the belongs to relation. So these are two different purposes. Yeah, the n refers to more algebraic setting, whereas omega refers to the order relation. Okay. So look here. Yeah, this is your first glimpse of the axiom of choice. Yeah. So in the class we have seen that product of two countable sets is countable. Yes. So therefore by induction, if you may, yeah, product of finitely many countable sets is countable. Well, what are the elements of finite Cartesian products? They are ordered tuples. Yeah, ordered pairs we have seen Kuratowski's definition. Ordered tuples you can do similar way. Yeah, singleton x1, then doubleton x1, x2, then tripleton x1, x2, x3 and so on. Yeah, or maybe you have to use some other definition, but you can do that. However, now the question is how to define infinite Cartesian product. Okay, so infinite Cartesian product is not something easy to do set theoretically. So for that we need to start with an infinite family of non-empty sets. So why non-empty? Because if at all one of the sets turns out to be empty, then yeah, it's like multiplication by 0. Yeah, everything will simply vanish, so we don't want that to happen. So we'll start with an infinite family of non-empty sets. So that means capital I is an infinite set, right? A choice function on this family is defined to be a function from capital I to the union of xi's. Union of any family is always defined. Yeah, I mean if I call this family Y, then this is simply union of Y. Family and set are not different. It just for our convenience I am calling this a family. Okay. So a choice function on this family is such a function such that it satisfies one peculiar property, that Ci is in Xi. Well, you want to select, you want to choose infinitely many elements, but you always want to choose them appropriately. For ith index you should choose it from Xi. For I prime you should choose it from Xi prime. So definition is clear. This is a choice function. Now what is the Cartesian product? The Cartesian product is collection of all choice functions. Yeah, this looks very weird. I mean normally how would you write a Cartesian product? You will like infinite tuple. Right? When you write a sequence, then you would say that it's infinite tuple. But that tuple has this property, right? That A1 belongs to capital A1, B1 belongs to capital B, A2 belongs to capital A2 and so on. So again, to give meaning to so on, we have to do it properly using choice functions. So that's the only requirement for understanding this. Now the next question is this countable? What do you think? Is infinite product of countable sets countable? Well, the real answer is, before knowing anything about it, yeah, does this choice function exist? Right? So that depends. I mean in general, yeah, I mean if I'm not talking about natural numbers, I don't know anything about the sets xi. So in that case I have no idea whether such a choice function exists or not. Axiom of choice is the statement which ensures existence of at least one choice function. However, let's not go there, that will come later, but we want to understand whether product of natural numbers, infinite product of natural numbers indexed by natural numbers, is that countable? What's your feeling? No? Yeah, we are assuming axiom of choice, so he is saying no, you are saying yes. Yes, do you have any proof? Yesterday in the class I covered that assuming countable axiom of choice, countable union of countably infinite sets is countably infinite. Countable union. I never said anything about products because products are defined today.
Like informally, like suppose you do have a bijection, you can like go along the diagonal and.
Correct. Okay, so he is referring to Cantor's diagonal argument again. Let us do it properly for another function, another set. Yeah, so this is this set of functions from natural numbers to natural numbers countable? Yeah, so this is a famous Cantor's diagonal argument. Okay, so Cantor's arguments usually involve contradictions. So let us start with the assumption that suppose this is countable. Okay, suppose this is countable. Then what can we say about this? Then there exists a bijection, bijection between this set and natural numbers. So which means I can say that this is the 0th entry, this is the first entry and so on. Yeah, then all such functions can be listed. Say f0, f1, f2 and dot dot dot. Yeah, this is the complete list of elements of all such functions. Now the trick, the Cantor's diagonal argument is a trick. It says that suppose this is a complete list, then I will construct a new function which is not in the list. How do we ensure that? A function which is not in this list.
Like f of take the 0, like say the function is h. H of 0 would be f of f0 of
Define h, okay, define h from n to n.
Yeah. H of 0 would be f0 of 0 plus 1 and so on.
Okay, so I am going to say it is fn of n plus. Yeah, fn of n plus. Define this. And now I am going to claim, this is the Cantor's diagonal argument, that you are defining something which is different from everything. Yeah, so claim that h is not in the list. So we have already listed all the elements. So h is not in the list. Why?
It is different from the kh function.
Exactly. So clearly h is not equal to fn for h of n is not equal to fn of n for any n. And that's the argument. Yeah, so if we said that we have listed all the functions from natural numbers to natural numbers, then we found one more function which was not listed. Well, you could say that let's add this function to the list. Yeah, why not? Yeah, before f0, let's make more space, let's call it f minus 1. But then again there will exist another function by the same argument, and this process will never end. So this shows that functions from n to n is uncountable. Now why diagonal? Let me quickly write that. So look at this, f0 of 0, then f0 of 1 and dot dot dot, then f1 of 0, f1 of 1 and dot dot dot, f2 of 0, and so we are taking the diagonal and we are disturbing the diagonal. Yeah, by saying plus 1, we are disturbing the diagonal. So that's why this is called Cantor's diagonal argument. We are playing with the diagonal.
Can we write it more formally, like you said that we can add this, so how to write it more formally and we have used dot dot dot, like more abstractly, like...
Oh, I mean, see, then list all such functions is saying same thing as there exists a bijection from natural numbers to functions from n to n. It's a particular bijection. Yeah, and if it is a bijection, then we have listed all the elements. Yeah, I mean functions of, it is surjective. So all functions have been considered, so where is this function coming from? Right, so understood this idea? Now can you use the same idea to prove the previous one? Is the product of natural numbers.
You can identify the union with one of the functions on n.
Identify which union with which function?
In the Cartesian, the choice function is a function from the naturals to the naturals, right?
Choice function is a function from naturals to naturals, yes.
So this is essentially the same as asking if the set of all choice functions is countable or not.
However, in this case, the choice functions are all functions also. See, in this case, yeah, here, union of n, where n belongs to n, is equal to n, and I is also equal to n.
And then we already solved it, right?
And therefore, yeah, therefore what will happen? A choice function is any function. And therefore, this product of n indexed by natural numbers is same as fun n n. And we already solved the problem for this. Understood? Simple argument. Let's stop.